hardcore predicates, which we started seeing in the last class. So let me find it comforting to write down what I'm going to do. Two topics today, which is continuing from the last class, the Goldreich-Levin theorem, which, as the slide says, it gives you a hardcore predicate, one hardcore predicate for every one-way function, as opposed to sort of searching for the most, least, who knows what hardcore predicate. That's number one. Number two, hope we'll have time, if not we'll continue in the next class. We'll see how to use these hardcore predicates to get pseudo-random generators. That's really, I mean, that's a killer application for hardcore bits, and that we need to start seeing pseudo-random generators. And just to give you a sort of a look into what lies sort of epsilon ahead in the class. We'll build use pseudo-random generators to construct pseudo-random functions, in other words, block ciphers, which will give us symmetric key encryption, beating Shannon in some sense. So Shannon told us that you need long keys as long as the message. We'll be able to do short keys to encrypt very long messages. That's what will come up, and then on and on and on. Okay, so that's the idea. Okay, so these are the two topics, 1 and 2. All right, so we saw that for the discrete log of one-way function, the most significant bit is hardcore. Most significant bit, again, has to be appropriately defined, not the obvious one, right? It's, whether the input lies in the first half of the domain or not is the right most significant bit. For the RSA one-way function, it turns out that the least significant bit is hardcore. It also turns out that the most significant bit is hardcore. Well, it also turns out that pretty much every other bit is hardcore. And you'll do it. You'll do one of these problems in the problem set, next problem set. What we're going to do today is the universal hardcore Goldreich-Levin. So before we go there, let's sort of remind ourselves, so reload in our head the definition of hardcore predicate. So given a one-way function f, which is maps strings to strings, let's say. A hardcore predicate is a Boolean function. It's mainly a function that outputs one bit. That is easy to compute given x, just like f. F is easy to compute given x, b is easy to compute given x. It's a Boolean function. But given f of x, it's hard to come up with x. That's what one-way function says. And given f of x, it's also hard to predict p of x. Not just come up with the right answer with like 25% probability, because it's a bit, right? I mean, it has to be really very hard to predict. I can always sort of come up with the right answer with probably 50%. So it has to be hard to do any better than 50%. Essentially, half plus negligible is the best you could do. Any others. So that's hard. So any questions before we sort of dive in? All good? All good. Going once? Okay, so this is the object of study today. Okay, so here's the theorem. It's a magnificent theorem. It's really, there are, like the story of blind man and the elephant, right? I mean, this is an elephant that several people have looked at from several angles, and they've seen several things. So coding theorists look at it and say, list decodable codes, okay? Learning theorists look at it and say, here is an algorithm for learning linear functions, whatever that means. Okay, so, and so on and so on and so on. Fourier analysts, people look at it and say, this is something else. Okay? So it's a beautiful, beautiful theorem. But for us, it originated from cryptography, and that's the context in which we'll sort of study it. Okay? So here is the one function that dominates all functions. That is a hardcore predicate for every function. And that is the, yes? No, good. So here's the function. Now I cheated a little bit. what I'm going to give you is a family of functions, not a single function, not a single predicate, but a family of predicates, such that if you choose a random predicate from the family, it is hardcore. Okay, so what do I mean by this? The family of predicates is indexed by a random R, right? So for every R, there is a predicate. And for an R, what the predicate does is it takes as input x, the same x as the one-way function, okay? And it computes the inner product of x and R. That's what it is. It's not one predicate, right? It's a, for every R, right, given f of x, yes? I mean, the function, the hardcore predicate is not just a function of x. It's also a function of R. But where does this R come from? R, you should think about it as indexing a family of predicates. Right? So when we think about it, is you have a family of predicates, B sub R of x, which outputs R in a product x, mod 2. Right? So, which is the sum of Ri xi mod 2 by definition. Yes, so this is a indexed by R in 0, 1. Again, assuming that x is an input string. This is a family of functions, family of predicates, such that if I give you a random predicate from this family, pick a random R that's a random predicate from this family, is hardcore for every model. That's one way to interpret. So that's the one way in which what I said and what I'm now going to show is a bit different. Another way to interpret the Goldreich-Levin theorem is that you can take any one-way function f, right? Any one-way function f. You can construct another one-way function f prime. What is f prime? F prime takes x and r, it computes f of x, and it just outputs r. Okay. So what is the point? The point is that the Goldreich-Levin predicate is one hardcore predicate. So now I can think about the Goldreich-Levin predicate as a predicate as a function of x and r together. And what does this predicate compute? It computes the inner product of x and r. That's one function now, right? Which is hardcore for, not for f, but for this f prime. So there are two different ways to kind of interpret, equivalent ways to interpret the Goldreich-Levin. Yes, same thing.
I'm sorry, what are the double bars signify for f of x?
Which double bar?
Concatenation.
Concatenation.
Okay.
Right? So, it's a stupid function, right? I mean, it says, let me think of my input as 2 n bits. The first n bits, I'll do something interesting, namely compute a one-way function. The second n bits, just output it as. Why am I doing it? Because I want to define a single function which treats R as the randomness, or yeah.
So did you say that function f has to be length preserving?
The function doesn't have to be length preserved. No.
So what if R is all zeros and then a 1 at the very end? Then R is, this b sub R of x is essentially the significant bit.
Yes, that's correct. That's correct.
And you're saying that the significant bit.
That's not what I'm saying. Right?
Okay.
I'm saying for a random R, yes, for a random R, the inner product of R inner product x is a hardcore bit. Yes. So think about this function. There are two ways to interpret it. Let's think about this function.
Okay.
What does it mean for the inner product of the first and the second half, right, to be hardcore? It means that if I give you a random f of x comma r, pick a random x and r, give you f of x, f prime of x comma r, you should not be able to predict x inner product r. Okay? The guarantee only holds for a random r. It doesn't say, what is the chance that if you pick a random r, an n-bit string, you would get one that is 0, 0, 0, 0,
So
0.
it's probably a hardcore predicate.
No, it's a...
For f. B sub R of x.
The right way to think about it is that the inner product of x and r is a hardcore predicate for f prime in the same sense that we defined in the pattern. In other words, if I give you f prime of x comma r, right, which is basically f of x comma r, the probability that you can predict R in a product X is half, essentially. It's half plus negligible, no better than that. Yeah? That's what it is. Right? It's just as good as a hardcore bet for any application you can think of, including sort of randomness appeal, including the coin tossing application that we saw. Just exactly. Anything? Any other questions? Good? So let's see. Okay, this is the function. So maybe one way to kind of, oh, that's not very good. One way to interpret this is the right way, the cleanest way probably to interpret it is as this. Take any function f, you can create another function, which is z prime, for which the inner product is hardcore, just like we defined. All right, so you see, it's not, it doesn't say anything about any fixed bit of x, any fixed, this thing, the most significant. It's basically a parity, right? If you think about it. So what is the inner product of x and r for a random r? It's a parity of a random subset of the bits of x. Yes? You see that? Yes? So, inner product is the sum of ri xi. Yes? Sum is what? Mod 2 sum is parity. Yes? XOR. That's what it is. XOR of ri xi. When r, what do these ri's do? These ri's are 0 or 1, randomly. Okay? So if you look at ri's which are 0, they don't do anything. They multiply out, they get 0. If you look at the ri's that are 1, right, which is a random subset, which indexes a random subset of 1, 2, 3, up to n, you basically pick out these xi's, the xi's that occur in this random subset, and parity, XOR them together. So it's a parity of a random subset of the bits of x. That's what this is. So it doesn't say anything about any fixed bit, it says a parity of a random subset of bits is hardcore. That's what it is. Good? In a sense, yes.
Why is it required that r be the same length as x there?
Because I need to compute the inner product. Right?
But
The inner product is the sum of xi I take. Right? To compute the inner product, the scalar product of two vectors, they have to be of the same length.
But to get only a single bit in the end, would you not be able to just
This gives you a single bit.
Yeah, but you could just sum up all of the bits of x and then...
Sum up all of the bits of x. Okay, so you know what? Okay, let's see for a second, okay? So if that would work. I claim it wouldn't, in the following sense. If instead, I didn't do this crazy business of r and so on, so suppose p of x is the sum or XOR, all the same thing. Okay, sum is going to be XOR for this class of xi, mod 2. Okay, so this is the sum of all the bits, parity of all the bits. Is p of x hardcore for all one-way functions? Yeah, that's the kind of thing I want to prove. Yeah, so that's the kind of thing I want to prove. Is that true? How many people think yes? I didn't think so. How many people think yes? How many people think no? Whoa. Okay, you better have a reason why. Why? Why? Why not? Yes.
We can use the same type of trick we use for the homework problems. We can take some f and make another f out of it. That has
You
one.
didn't ask this as a homework problem, right, Salid? No, okay, good. All right. Okay.
That has XOR always 1, for instance, fx, and then one more bit that fixes the XOR.
Good, good. So here is what, what's your name again?
Arsene?
Arsene. He's saying is the following. This cannot be true. Why? Because if I am going to construct a one-way function f for which this bit is not hardcore, how do I do that? Okay. So say if that type of trick is in class, assume that there exist one-way functions, okay, some f prime. Okay, so I don't know what it is. I have no clue. Just give me just claim that there exist one-way functions. I called it f prime. That's all I do. Okay. From this, I'm going to construct a function f, which is also one-way, but for which this guy is not hardcore. How do I do that? F of x is f prime of x concatenated with b of x. Okay. I claim that number one, this is one way. Homework exercise, you can prove it, because I'm only giving you one more bit, yes? Not much information. So if you can invert f of x with probability 1 over p of n, you can invert f prime of x with probability 1 over 2 p of n. You lose a factor of 2. Right? So if f can be inverted, f prime can be written. In other words, f is one way. But clearly, b of x is not hardcore because one of the output bits of the function is b of x. Okay? So given the output of f, b of x is not hard to predict because I can read it off. So it's a good question, very good question, and a corollary of this construction, which you can easily extend, is that no single function can be hardcore for all one-way functions. This kind of construction would basically kill every single function. So you need a family of functions. That's what that does. Or you have to change the function in this way to basically kill this construction. Yeah? So that's what we're learning. There are two different ways of seeing it. That perspective says it's not a single one-way function. Sorry, not a single predicate. I pick the predicate after you told me what the function is, and I pick it at random. So, yes.
Okay, so if you pick the predicate at random, then you type probability into the partial predicate?
So you can make that kind of claim. You're not going to do it. So you say for most R's, right? R's. These guys are hardcore. For every one-way function, more than sort of 51% of the R's are hardcore. But these R's depend on the one-way function somehow. So because if you fix any R, I can kill it. So it's very delicate, extremely delicate. Okay, there's a beautiful open problem here, but in the interest of time, if you want to ask me about it, ask me after class. Really, anyway, I'll leave it at that. Okay. So this is why you need a family. You cannot have a single function. You cannot have a single predicate. Okay, so how do we prove this kind of state? Okay, we'll do the same thing as before. Let's assume that there's a perfect predictor, which says what? You're given the output of f prime of x comma r. In other words, it's f of x comma r. That's what f prime of x comma r. So that's what you're given. And you have to predict x in a product r. And then the guy predicts x in a product r with probability 1, let's say. Namely, for every x and r, he gives you the right answer. Okay. So now, why are we doing it? Because we want to say that contrapositive, right? I mean, we want to say if it's a one-way function, there are no good predictors. Contrapositive, we want to say if there is a good predictor, then I will invert the one-way function, and therefore contradiction. That's what we want. So now we say, suppose there is a predictor. Really, we only have a pretty crappy predictor, right? Half plus epsilon. But you know what? Between friends, okay, let's say we start with a perfect predictor. Okay, this is what the guy does. How do I use this guy to invert f? In other words, come up with x or some inverse. How do we do that? Any thoughts? So look, I mean, what can I do with this predictor? Yes. I'll give.
I mean, you can compute the f dot product of x with x bar, and that gives you x uniquely.
Very nice. Except there are too many r's. How many r's are there? 2 to the n.
Yeah, we only need n.
Right. Any other solutions? Yes?
Oh, just like try 1, 0, 0, 0, then 0, 1, 0, 0.
Those are n vectors with good, excellent, beautiful. Okay, so all right, yeah, that would indeed work. Let me make life a little more complicated or interesting, looking ahead to what we are going to do with inverter. Okay, does everyone understand what the solution here is? So this inverter, this guy says, look, I'm only getting f of x and r, and I'll give you x in a product with r. Okay, that's what this guy, for every x and r. So now you feed r equals the first unit vector, namely 1, 0, 0, 0, 0, 0. What will he give me? The first bit of x. You feed him 0, 1, 0, 0, 0, 0. What will he give me? Second bit of x. Do it n times, you get x. Beautiful. But that only works for a perfect predictor. In particular, an imperfect predictor could refuse to answer for these NRs. He'll only answer for a random R, yes? I mean, he can get away with not answering for any fixed sequence of N. Guys, and still get a non-negligible, still get a sort of an advantage, non-negligible advantage. Yes? N is a very small number compared to 2 to the N. I can say no for N and I can do well for the N. So we'll look ahead and we'll do, and this is the deep identity that we are going to use. Okay, so X inner product R, you know what it is. R XOR EJ. E sub j is the unit vector. Which is 1 at the jth location and 0 everywhere else. Okay, that's E sub j. R XOR E sub j is simply R with the jth bit flipped. Okay? The XOR of these two, by linearity, is X inner product E sub j, which is X sub j. That's a deep lemma. But, given this lemma, what do we do? This is somewhat more complicated than the suggestions here, but we'll need this. We'll need this one. So what do? I pick a random R. I ask the predictor for, give me the inner product of R and X, and give me the inner product of R plus EJ and X. XOR, he'll give me the answers, XOR them together, I get the J vector. Repeat for every J. Is it clear? What's going on? Okay. Good. Good. That's not the fact of life. Yes, the predictor is not perfect. We only know that he succeeds slightly better than half, 51%, in fact even worse, half plus 1 over polynomial, for some polynomial. Yes, that's all he does. This is the opposite of, this is the negation of saying that, the predictor only succeeds with negligible probability. The opposite of that is that there is a 1 over polynomial such that the predictor succeeds with half plus 1. That's all I know. How do I use this guy? Okay, so here's what I'm going to do. I am going to feed this predictor many things. Many things. And every time I give him something, it's going to be the same x. It's going to be the same f of x. I'm not going to change it at all. Why am I not going to change it at all? Because I don't know how to change f of x in a way that it maintains some relationship to the origin of x. Yes, from f of x, I don't know how to compute f of x plus 1. For an arbitrary one function, are you kidding me? I mean, right? For discrete log, maybe, but not arbitrary. So I'm going to feed him with the same f of x, but change the r. It's the only possible strategy for general one functions. Okay, so step one, I'm going to do what's called an averaging argument that says that if that is true, if the top statement is true, then for a good enough fraction of the x's, the adversary is going to predict the inner product with a good enough advantage. Good enough is, used to be 1 over p of n before, it deteriorates to 1/2, 1 over 2p of n, not a big deal. But this is going to work for 1 over 2p of n fraction of the x's. Yeah, this sort of thing is called an averaging argument. So why is this true? It's a manipulation of probabilities. Right? So suppose this were not true, then I would contradict the statement above. Right? Yeah? Okay, so what? So proof of... So you see why we are doing this though, right? Because we are going to feed the adversary with the same f of x. Maybe random and independent r's, but the same f of x every time. And we want to argue something about the independence of these events, right? So otherwise, who knows what happens. The r's I'll choose randomly or somewhat randomly, as we go along, so I will be able to argue independence. But the f of x is the same guy, so I want to fix this guy and then continue the experiment after. That's why I'm doing this funny business. Yes? Yeah? Proof of averaging argument. So suppose the claim were not true. Yes, that claim is not true. I'm going to contradict the guy on the top, statement on the top. How do I do it? Say, what is it? Let's calculate the probability that the predictor yes. This is at most, I claim, well, let's look at these x's where the advantage is significantly large. Call them good x's. Call them good x's. So let's say this probability is equal to the probability, the same thing, given that x is good, times the probability that x is good, plus just conditional probabilities. Okay. We, was a claim we're not true, right? That's where we're starting from. So the fraction of good x's is at most 1 over 2p of n. Right? This is the probability x is good. And if x is good, what is the probability that the prediction is correct? At most 1. Cannot be more than 1. Yes? So this is this, and this is this. Plus, what is the probability of success when given x is bad? My hypothesis, right, smaller than or equal to this. Yes. No, let me say. So what is the probability that x is bad? Well, 1 minus 1 over 2p of n. Right? And given that x is bad, what is the probability of success? It's at most half plus 1 over 2p. Okay. So this is strictly less than half plus 1 over p of n, contradicting the fact that the adversary actually succeeds. So it's conditional probability. It's counting. Okay. Simple. Just you can reproduce. You know what probability means and what conditional probability means. Yeah? So what I'm doing is I'm decomposing the R and X. I'm saying, let's sort of decompose the probability statement into the one with X and one with R. And one with X, I'm going to say for many X's, I'm going to solve with a for random R. With half plus. Good? So I'm to say this class is going to be heavy probability. Okay. So I would recommend that you go back and you think about it deeply. Yeah? That's the nature of the beast. Okay. So now let's see. Okay. Well, now that I said probability, I have to So let's take a quick detour into probability, and let me ask you this puzzle question. Yes.
Is this for a fixed x? This probability.
Okay. Good. So now what this claim says is that if you look at the world of all x's, right? All x's, there is a set of good x's. Right? What does a good x mean? A good x is one where, the probability over R alone that the adversary predicts this guy is more than half. Right? Half. Before it was, if it was 52%, now it's 51%. So later in the analysis, we are going to say the bad x's, I'm going to ignore them. I'm never going to invert the function on bad x's. There are a lot of bad x's. 1 minus 1 over 2p of n bad x's. So I'm going to fail all the time. But I'm going to succeed for 1 over polynomial fraction in inverting. And that's good enough to break a wonder function. I'm giving up a lot, but not that much. Yeah?
So is that probability that you're getting from the claim over R and X, or just R at the beginning?
Good. So this is what comes out of the claim, right? Yeah. So I'm saying, if the claim were not true, right? Let me recompute the probability up top over R and X, right? And that, Okay, thanks. Beautiful. Okay. So, yes.
Why is the probability that is bad is less than 1 minus 1 over 2 polynomial n?
This guy?
Yeah.
So let's for a moment say, you know what, it's certainly, well, so let's for a moment say that the fraction of good x's is exactly 1 over 2pfn. Right, so that is the 1 over 2pfn, the good x's here, and the fraction of bad x's is the opposite of that, 1 minus 1 over 2pfn. Right? If it's not exactly 1 over 2pfn, if it's small, if this number is smaller, then, you know, let's replace this by 1. Okay, can't be any more than 1, right? Still I would get the contradiction, right? So 1 times half plus 1 over 2pfn plus 1 over 2pfn is 1 half plus 1 over pfn. Still, it's less than or equal to, and that contradicts the top. Yeah, good point, good catch. I'm being a little stoppy, so good to check. Yeah, good. All right, so here are, I don't know, Google interview questions, okay? Right, so, puzzle problems. Okay, so I give you coin tosses, a sequence of independent coin tosses, m of them, m of independent coin tosses. Either of these coins are all tails, okay, yeah, this is a very biased coin, or it's heads with probability epsilon. I don't tell you what is the case, I just kind of toss these coins, right, one of either one type or the other, and I give you these coin tosses. You have to decide which coin did I toss. The all tails coin or the epsilon heads coin. Okay, and you have to decide, you have to be correct with probability 90%, let's say, or you know, stretch it 1 minus delta for a very small. How many coins do you have to toss? Yes? 1 over epsilon. So we're not going to care about constants, so theta 1 over epsilon. Yes? Yeah? And what is the algorithm? What is the distinguisher algorithm? What is the guy that predicts correctly? Anyone else? Is obvious one, yeah?
Is there a
Good. Yeah, I mean, but what else? I'm all set. I sum them up, and I get x inner product ej, which is the j. What is the probability that the predictor is correct on both these guys? Hey, you know, it's pretty good, right? Because, well, how can I be incorrect here? If the predictor gives me the right answer for both, I'm all set. If the predictor gives me the wrong answer on both, I'm also all set. Yes? Yeah, because the predictor gives me x inner product r XOR 1. It's a compliment. He gives me x inner product r plus ej XOR 1. But 1 XOR 1 is 0. So that is beautiful, right? But really for now I'm just going to use, you know, even if I use the simpler analysis where I say, well, you know, he's correct on both, I'll still win. So I'm just going to use that. I'm not using the full power. So how do you analyze this kind of thing? So what is the probability that the predictor is correct on R and is correct on R plus J? I want to say that this is at least something, right? Yeah? Do I analyze this? I can't use independence. I just cannot use independence because R and R plus EJ are not pretty not independent. Yes, that. They're not even pairwise independent. I mean, if I look at both, I know. So the only thing I can use is something called the union bound. Okay, and we'll get that in a second. Oh, so the union bound, yeah. So let me analyze the opposite. What is the probability that the predictor is incorrect on either R or R plus EJ? I want to say that this is at most something. Right? And it's the same thing. I can flip the two. So this is at most the probability that he's incorrect on R, plus the probability that he's incorrect on R plus EJ. Right? So that it cannot be more than that. He could be incorrect on both, but I'm overcounting. Yeah, so this is at most what? So what is the probability that he's incorrect on a random R from that? Help me out. Coffee is very done. Yes.
Like 1 minus 3/4.
Correct, correct. Which is 1/4 minus 1 over P of n, right? Correct. So it's 1/4 minus 1 over P of n. What is the probability that he's incorrect on R plus EIJ? It's a separate event. But R, if R is random, R plus EJ is also random. The same number. 1 over P of n, which is at most a half minus 2 over P of n. Yes? This is the probability that he is incorrect on either one or the other. Which means that the opposite, the probability the predictor is correct on both R and R plus EJ is at least 1 minus that, which is half plus 2 over P of n. Yes? And if he is correct on both R and R plus EJ, I get the value of xj correctly. So, probability that xj is correct in one iteration of this sufficiently many times. So every time I pick R into this experiment, the probability that I get the correct xj is better than 1. Okay? By 1 over 2 over 3. So now I'm in the coin tossing game. Right? I repeat this experiment enough times. I get the right value of xj with more than half plus 1 over P of n, 2 over P of n times. I get the wrong value with the opposite. So if I take the majority of the number of the bits I get, I'll be good. Okay, so this is the bias. You know, the experiment that we did, this is the epsilon bias. We think of it as coin tosses, which happen with epsilon bias, right? The number of times I have to do this is sufficiently many, is, you can compute what it is. Sufficiently many is a theta 1 over epsilon squared log 1 over delta. I haven't said what delta is, so let's say I want that the probability that the majority is correct. I want it to be very large. I want to be very good with predicting this. So let's say 1 minus 1 over n squared. Really very good. Yeah. So this is delta. And that's epsilon, so you can compute what this is. So this is roughly P of n squared log n. Yes? 1 over epsilon is P of n, 1 over epsilon squared is P of n squared. Log 1 over delta is log n. Okay? So if you do, so this is, my point is that this is a polynomial number of samples. Sufficiently many is not exponential. Sufficiently many is these many polynomial samples. If you toss them, you take the majority, you get the right answer with very good probability for 1 bit. So now I do this again for each bit of x. What is the probability eventually that I get any one of these bits wrong? What is the probability that I get the first bit wrong? 1 over n squared, delta. What is the probability that I get the second bit wrong? 1 over n squared. What is the probability that I get one of these bits wrong? Again, union bound. At most n over n squared, so 1 over n. So the probability that I get all of the bits right is 1 minus 1 over n, which is pretty good. I mean, I'm not inverting. Yeah, in these good x's, I'm inverting with really good probability. Probability that xj is correct is at least 1 minus 1 over n squared. So this is right from here. Probability that all xj are correct is at least 1 minus 1 over n, again by unit bound. Yes? So this is the same as the probability that x is correct. Yes, I inverted the whole x. So for every good x, this is true. Yes? So why every good x? Because I assumed that these are x's where the predictor does pretty well. Yeah? Bad x's, I couldn't give it down. Okay? So overall, what is the probability that I invert correctly? Is at least the probability that x is good. So that's 1 over 2p of n. And for these good x's, I invert with probability 1 minus 1 over n. So this is at least 1 over 3p of n. So for large enough n. That's good. That I inverted. I inverted the thing. Yes? We declare victory. We declare victory. Except one of you should catch me. I made an assumption here that the predictor is 3/4 good. Is not the case. Okay, so no matter how I imagine that predictors are nice and honest and behave 3/4 correctly, it's not the case. So what do I do? No. You do more math. There is no way out of math.
Why did you fix your basis to be this basis?
It doesn't have to be the EI basis. It could be any sort of bit. Yeah, you're right.
So when you get around this 3/4 probability,
That's not so. Where, you know what? Where does the 3/4 come up?
because you have to subtract, so you have to take x, r, and x,
Let me think about that. Very good. Okay. You're saying let this be a random vector. Then I get the inner product correctly with probability this of 1/2 plus. But then I have to repeat this many, many times. Yeah, follow many, many times. And I want independence. No? So what are you going to do? So this is one experiment. I pick an R, and I do R plus this vector that you picked, right? The next time I pick R prime and R prime plus the same vector you picked. Has to be.
Well, I mean, so I can just pick n vectors.
But then how do you get what value do you get? You can't compute majority. Majority works if you get the same value with independent noise. Yes?
Wait, so we only need one correct S comma R, right? We don't do the majority.
But I need to get the right answer eventually. Each bit I want to be correct with a very large program. Otherwise, I'm only going to get a fraction of the bits correct.
Oh.
Right? So how do I get each bit very well? I want to do many sort of iterations, take majority. Majority of what? If it's the same bit, if it's x in a product, the same basis vector, noisy a little bit, then you take majority, you get the right answer. But if it's many basis vectors, I don't see how to. Yeah, Alex? Yeah. So if Alex says, my TAs say, can't do better, I suppose you can't do better. Let's, all right. Pairwise independence. Okay, so I want to do better. I want to handle adversaries that really do the minimal thing possible. how do I win here? Really, this 3/4, this is very annoying. It's extremely annoying. Let's try to get rid of it. Here's one way to get rid of it. I pick all these r's, right? Pick all these r's. I am going to guess x in a product r for all these r's. Yes? I'm going to guess them. Now, either all my guesses are correct, in which case I will argue something, or my guesses are wrong, in which case I have nothing to argue. I lose. So why am I doing this? Because let's say you condition on the event that all my guesses of x in a product are, so this is meaning this computes x in a product r, this computes x in a product. Let's say all my guesses of x in a product are correct. Condition on that event. Yeah? When this guy goes away, there is no or, this is 1. Okay? I conditioned on that event. I'm cheating here, but I conditioned on that event. Yeah. So then this probability, there is no 1/4, there is no nothing. This becomes really, this is really half minus 1 over the event. That's the probability that I'm incorrect on this quantity, this bit. So the probability that I'm correct is half plus 1 over. So I get a signal here. Now I compute the majority. Everything works exactly the same way. But I cheated. I cheated big time. Why? Because eventually my probability of success is the probability that all this works out conditioned on all my guesses being correct, times the probability that all my guesses are correct. What is the probability that I can guess all these? It doesn't make any sense. It's like guessing x. Okay, it doesn't make any sense. Yes, doesn't make any sense. So, what am I doing? Here's what I'm doing. For this whole analysis to work, I'm going to give you a high-level idea. Okay, so if you have questions, please ask. For this whole analysis to work, I never needed these r's to be completely random. I only needed them to be pairwise independent. So, why? Where did this difference come up? It's pairwise independent versus completely random. This never comes up because I assumed no independence between these two things. I assumed nothing for this calculation. There, I did assume, right? This comes out of Chernoff. Yes. Comes out of Chernoff. But you know what? Let's assume that I only have pairwise independence. These r's that I generate, somehow, if you look at all these r's, if you look at any pair, I will generate them in a minute in a way that any 2 are random and independent, but any 3, no guarantee. Those are my r's. So then, I am in what shape? So it's not Chernoff anymore, it's Chebyshev. Okay. And then if you do the calculation, I think I need not log n, but rather whatever I need here, 1 over delta, that's n squared. But you know what? Who cares between p of n squared and p of n squared times n squared? One is a polynomial the same as the other one. Okay, so I was overdoing things. I really only needed pairwise independence for this argument. This is step number 1. Okay, so these r's didn't have to be totally random. And indeed, if these r's were totally random, and I tried to do this funny business, try to predict all x in a product r's correctly, there is no way I'm going to succeed. Clear? So here's what I want to do. I want to pick a small number of seed r's, very small number, logarithmic really. Yeah? I want to predict all these, so here's my strategy. Wait a minute. Now, so my strategy is the following. It's one of the first uses of pairwise independence in computer science, in theoretical computer science. It's really beautiful. Strategy, step 1. Pick a bunch of s's. S1, S2 up to S what? Log n. Okay? Roughly log n. guess x in a product S1, x in a product S2, x in a product S log m, the same m as before, whatever that this m. Yeah? And now expand, these are truly random, right? S1 after S log m, really truly random. It's a small number of guys, log of these guys. Expand SIs into m pairwise independent R1 and 2 R. Okay. So from this seed, I want to generate exponentially many guys. Of course, I cannot generate randomness out of everything, although I will contradict it in a few slides. Yeah, true randomness, I cannot generate out of nothing, but I will generate pairwise independence. Okay, so beauty number one. Okay, 3. If I predicted x in a product, all these SIs correctly, which happens with what probability? Each one is a bit. Yes. What is the probability that I predict all of them? 1/2, good for 1. 1/2 times 1/2, 1/2 to the log m. So 1/m probability, I would predict these guys correctly, all correctly. In fact, I could even enumerate all possible predictions. There are only 2 to the log m predictions, just enumerate the damn thing. That also I could. Here is the third beauty. I can now, okay, so I didn't tell you how to expand these SIs into this R, right? So each R, okay, is indexed by a subset. Okay, so T subset of log m. So each R, these indices, these sub-indices will be a subset of these log m bits, and I would basically pick these subset of S and sum them up. Okay? So R sub T is the sum of I in T. See what I'm saying? So I have a log m guys. I pick every possible subset of these guys. How many subsets are there? 2 to the log m guys. In other words, n. And each R is a sum of a distinct subset of these S's. And I now expanded things from log m to m. Yes, numbers work out. Log m to m. These are pairwise independent. Why? Let's look at 2 sets. Okay, so the set 1, 2. Right? So R sub 1, 2, and R sub 3, 4, or rather 2, 3. Okay, these guys intersect a lot. Yeah, I claim these 2 guys are independent, random and independent. Why? Because R12 is a sum of S1 and S2. Yeah, you sum 2 random vectors, you get a random vector. Okay. Conditioned on R12, what is R23? R2, S2 is fixed because I've already used it. But then there is a guy, S3, that I've not used, and that randomizes the entire. Okay, so you can check for yourself that any 2 subsets if you pick, as long as they're not distinct, there is a number that is contained in one but not the other. Yeah, so that's a practical. That gives you a okay. This is extremely beautiful. Yeah, this is expansion. And here's step 3. This is the way to pick up. If I predicted all these x in a product SIs correctly, I automatically predict x in a product all these R's. You see what I'm saying? So what is x in a product R sub T, let's say, indexed by T? It is x in a product with the sum of SI, I and T, which is, by linearity, the sum of x in a product SI, T. These guys I have computed myself. I am correct. I'm conditioning on the fact that I'm correct. So then I get R correct. And this is true for every T. I get all the x in a product numbers. Yeah? So there's a lot of things going on here. Okay. So my strategy at the end is going to be generate a huge number of R's. Okay. How? I generate a small number of S's and generate R's this way. Okay. 2, guess the values, or rather enumerate over all possible values of x in a product S1 and product x2 and x3, right? Okay. There aren't too many of them, there are m of them. For each sort of enumeration, run the predictor on R XOR EJ many times, take the majority. That'll give you the correct xj, the probability 1 minus 1 over n squared. Repeat for each j, you'll get all the xj's correctly, you'll get x squared. So this is all true if I guessed all these bits correctly. Otherwise, everything goes down. But you know what? I'm enumerating over all possibilities of these log n bits. So one of these things I will be correct, and then I will hit the right x. Then the whole inversion algorithm will give me the right inverse. Beauty number 4, which I will write down, is that you can check. Meaning, when you get the right inverse, you can check. You compute f in the forward direction, and you say, is it good or not? Yeah. Let's decompress. Okay. What is going on here? Lots of things going on. I recommend you go back and think about it. One, because there are two problems in the problem set concerning this. Not the whole thing, but will be. Yes, you can reveal it. You know, it's. Yes. So that's number one. Reason one, you should go back and learn. Reason two, just because it's super nice math. I don't know what to say. Yes. At the very least, I think you should sort of go back to warm-up 1 and really understand what is going on there. Really, truly, very well understand what's going on. And 2, I will go to warm-up 2, which I don't think is that bad either. Really, the kicker is when you, like the really sort of hard idea, I bet that, a constant fraction of you, large constant fraction of you would get warm-up 2 correctly by yourself. The real end game is really where the non-deterministic ideas come up. And for those of you who want to know, you should go back, think about it yourself, reconstruct it. Yes?
What is M?
Good. M here is the number of samples you need, which is one of them. So it's a polynomial, right? That's the point. Okay. All right. As if this is not enough. Well, actually, no. These guys, they, have all sorts of connections to coding theory. In particular, there is a notion of list decoding of error correcting codes. So error correcting codes, you know what it is, right? So I have a message, I encode it into a longer string, send it over. There are corruptions in a fraction of places, let's say a quarter of the places in the middle, right? And even if you get the corrupted code word, you should be able to recover the original message. That's error correcting. And the question is, what fraction of errors can you correct? Right? Half? Let's say these are bits. A half fraction of errors? There's no way. You just cannot do it. Okay? A quarter, you can correct it uniquely, in the sense you will recover the exact thing that there are techniques to sort of encode and decode. Right? Less than a quarter, you can recover correctly. But what if the error rate is very, very close to a half? Let's say half minus 1 over p of n. For some problem. It turns out that we can't recover the exact message correctly, but you can recover a small list of messages, of which one of them is the message I sent. So that's called list decoding. And really, at the core of what we are doing here, Goldreich Levin, is a list decoding algorithm. Is an error correcting code together with the list decoding algorithm. What is the error correcting code? Here's the error correcting code. X is your message. The code is X in a product, the first vector, comma, X in a product with the second vector, comma, X in a product with the third vector. How many vectors are there? 2 to the n. So the code that expands n bits to 2 to the n bits. It's a pretty horrible code from that point of view. The rate is horrible. So the error correction capabilities are excellent. Even if the adversary corrupts half minus tiny bit of bits, you can still recover. That's the coding theory point of view of correct level. And really, list decoding kind of originated out of this cryptographic result. So, okay, so, all right, so let's relax a bit. So pseudo-randomness. Okay, so this is the application, the canonical application of hardcore bits is to go from one-way functions. Suppose you have one-way functions, you want to go to a pseudo-random. You want to construct a pseudo-random generator, which we'll define in a minute, and that's where hardcore predicates come. That's the whole thing was a stage for this. Okay. So randomness we need. You need for algorithms, right? I need for cryptography because without randomness, there's nothing. Keys have to be random, right? I have to have some information that the adversary doesn't know, and if I don't have randomness, I have no way of generating that information. How do you get randomness? That's outside my specialty, but you can, dev random. Okay, but where does dev random get its randomness from? Noise, typing on the keyboard, transistor noise, all sorts of things. But this is expensive. Typically, you don't get true random bits, you only get entropy, some randomness somewhere. Then you have to, first of all, distill it into truly random bits. That's something you have to do. But in any case, it's very expensive, right? So it would be great if you can take a small amount of random bits, 128 bits, okay, and expand it into a very long string that looks random for all practical purposes. Well, how long? I don't care, 1,000,000 bits. Okay. Very, very long bit, a sequence of bits. That sequence of bits is not truly random. It cannot be. I mean, I cannot take 128 bits and deterministically generate 1,000,000 bits that are random. It doesn't make any sense. Classically, okay. But I can generate these 1,000,000 bits that look, to any polynomial time algorithm, it looks as if it is truly random. That is pseudo-random. Okay, so this is what it is. These are deterministic algorithms that take a seed, small seed, 128 bits, and expand it into a long sequence of bits that look random. I'm going to define what look random is. Let me ask you, what does look random mean? I know you're tired. I'll let you off on this note. So first of all, can you see, if I take n bits here, and a deterministic procedure that outputs n plus 1 bits, even 1 bit more, the output cannot be truly random. Why? That's the even more basic question.
It's a deterministic program, so if your input space is like lambda n, then your output space is still lambda n.
Good, in the sense that if you look at the set of strings that this generator outputs, there can be at most 2 to the n, no more than that. So the set of strings that I'll see of the total space of n plus 1 bit strings, which are 2 to the n plus 1, I will only ever see 2 to the n strings. It's not wrong. So on the other hand, if I really had random n plus 1 bits, I would see every possible string. Tiny probability, but I would see it. So it cannot be truly random. It only has to be somehow looks random. You know what? I'll let you off on this note. Let's start next week fresh. Do go back and read up the hardcore bits. And go to office hours.